Hello everyone, and welcome back to some more remote learning. In this video, we're quickly going to go over limit laws and the squeeze theorem before we really jump into more of those limits of rational functions. So, there's some basic laws for limits that we were actually using in the previous worksheet. I just didn't really talk about them, but we will for these examples. Now, just as there are laws for basic operations between numbers and functions, we have limit laws for basic operations between limits. So below are different rules and examples of how to use each. Let's go ahead and take a look. The first law we'll discuss is the constant multiple law. So if I have the limit as x approaches a of some function, but I am multiplying that function by a constant, so by some real number, let's call that number c. So if I have c times f of x, the constant multiple law allows me to pull that c out in front. So I can take c and multiply it by the limit of f of x as x approaches a. Doing that quick example that I have on the right, the limit of 3x squared, I'll rewrite this as the limit as x approaches 4 of x squared, and I'll pull that 3 out in front because that's some constant that's multiplied by my function x squared. So I'll have 3 times, remember this is a polynomial, so I can plug a directly on into x. So I'll get 4 squared. 3 times 4 squared is 3 times 16, which is equal to 48. The next rule we'll go over is the sum rule. So if I have the limit as x approaches a of some function f of x plus a function g of x, well, I can split this limit up. I can write this as the limit of f of x as x approaches a plus the limit of g of x as x approaches a. So individually calculating the limit of each of those functions with addition in between. Scrolling over to our example, splitting this limit up, because of the addition, I have the limit of 3x squared as x goes to 4 plus the limit of 5x as x also approaches 4. Now we've actually already calculated this limit, the limit of 3x squared as x approaches 4. We pulled that 3 out using the constant multiple rule and got 48. So I'll have 48 for that limit plus, again, I'll use my constant multiple rule and pull that 5 out in front. So I'll have the limit of x as x approaches 4. That'll leave me with 5 times 4, which is 20. So 48 plus 5 times 4, which is 20, is going to give me 68. Now, similar to the sum rule is the difference rule. And lots of times I like to think of subtracting as adding a negative. So this is like an extension of that sum rule. If we have a limit where I have one function and I'm subtracting the other function, I can split that limit up with subtraction in between. So I'll take my limit as x approaches a of f of x minus g of x and split that up into two limits. So I'll have the limit of f of x as x approaches a minus the limit of g of x as x approaches a. And I made these examples straightforward so we don't have to do as much work. When we split this limit up, we'll have the limit of 3x squared as x approaches 4, which we've already calculated, and we're going to be subtracting the limit of 5x as x approaches 4, which we also already have calculated. This first limit was 48, and that second limit we got was 20. So as opposed to adding them like we did up above, we're just subtracting. 48 minus 20 is going to give us 28. The next rule we'll discuss is going to be the product rule. So if I have the limit as x approaches a of one function f of x times another function g of x, I can split this up into two separate limits with multiplication in between. So I'm going to have the limit as x approaches a of f of x, and I will multiply that by the limit of g of x as x approaches that same value a. So in this case, the limit of 3x squared times 5x as x approaches 4. I'll split that up to have the limit of 3x squared as x approaches 4 times the limit of 5x as x approaches 4, which I know how to calculate both of those because I've done that above. So this will be 48 times 20, and 48 times 20 is going to give me 960. And as a quick double check, as opposed to splitting this limit up, let's simplify the functions first. If I was to simplify this, I would get 3x squared times 5x, which would be 15x cubed. So this is the same as the limit of 15x cubed as x approaches 4. So if I plugged 4 right on in for x, I'd have 15 times 4 cubed. 4 cubed is 64, and when I multiply that by 15, I get 960. So I get the same result regardless of how I go about simplifying and solving. However, think about if we had one function that was some polynomial to, let's say, a degree of 3, and then another function that was a polynomial to a degree of 6. Envision having to expand those out in order to calculate the limit. That would be very tedious. However, if we know the individual limits of those functions, we'll just multiply them together. The quotient rule is very similar to the product rule, except now we're dividing. So if we have the limit of f of x over g of x as x approaches a, well, we can rewrite this as the limit of f of x as x approaches a over the limit of g of x as x approaches a. So if we were dividing those functions within the same limit, we can calculate the limit of the numerator and then divide that by the limit of the denominator. But in this case, we need to be sure that the limit of g of x as x approaches a does not equal 0. This denominator cannot equal 0 in order for this limit law to be utilized. So assuming that that denominator does not equal 0, we can go ahead and simplify to solve. So splitting this up, we'll take the limit of 3x squared as x approaches 4 and divide that by the limit of 5x as x approaches 4. And you'll see we already know that the numerator, that limit was 48 over my denominator, which was 20. 48 divided by 20 can indeed be simplified down because both are divisible by 4. That will be 12/5. Now we're moving on to the power rule. So if we have the limit of f of x and that function is all raised to the nth power as x approaches a, well, we can calculate the limit of f of x as x approaches a and then raise that to the power of n. So I'm going to take the limit of 3x squared as x approaches 4, which I know the answer to that, but I'll raise that to the third. So that limit inside was 48, so I'll have 48 to the third, which is going to be a fairly large number, 110,592. But I'm not even going to bother with writing that out since it's not something I can easily do in my head. But you can see that if we were to simplify first, if we cubed everything within here, we'd have 3 cubed, which would be 27, times x squared cubed, which would be x to the 6th. So that function would be 27x to the 6th inside of there. See what happens when you plug in 4 for that limit. You'll get the same exact answer. But again, like I mentioned up above, imagine if this was a long polynomial. Cubing a polynomial, depending on its degree, could be very tedious. But if you already know the limit of the inside, just take that evaluated limit and raise it to whatever power your function was originally raised to. And the last quick limit law we'll discuss is the root. And this is if we have the limit of the nth root of some function f of x as x approaches a. Very similar to that power law, we're going to take the limit of f of x as x approaches a and take the nth root of that evaluated limit. Now this is important because remember, what is the domain of the nth root of some function? Well, the domain of that nth root depends on whether n is odd or even. Because remember, if n is even, we cannot have negative numbers within that radical. So this limit root law would only hold true when n is even if I get a positive number for my limit within that root. If n was odd, it doesn't matter whether the limit within that root is positive or negative because the domain of odd roots is all real numbers. So just be careful when doing this, making sure if it is an even root that we have a positive number under that radical. So let's calculate the limit of the square root of 3x squared as x approaches 4. I'll have the limit of 3x squared as x approaches 4, and I'll take the square root of that. That's going to be equal to, I know that limit within that radical is equivalent to 48, so that's going to be equal to the square root of 48. And the square root of 48 can be simplified down as a radical because a perfect square fits within it. The square root of 48 can be written as the square root of 16 times 3, which would be 4 root 3. And those are just some basic limit laws that you're going to be able to apply to help you simplify down a limit before solving. However, always feel free to simplify your function before evaluating the limit. Sometimes that's the easier way to go. But like in all these examples, when I already knew what the limit of 3x squared was as x approached 4, or when I already had calculated the limit of 5x as x approached 4, why don't I just use those values and use the appropriate limit laws as operations come up between my functions that I'm taking the limit of. For now, however, let's move on to the squeeze theorem, which is also going to be helpful for calculating limits that are difficult to simplify. So let's think about what if we were trying to figure out a limit of some function g of x, but we don't know how to take its limit. We can't simplify it down, we can't get that denominator to cancel out, we don't know how to do it. Well, if it's trapped between two other functions, some function f of x and some function h of x, then we may be able to figure out that limit of g of x depending on the limits of f of x and h of x, those limits that g of x is trapped in between. So again, if f of x is always less than or equal to g of x, and that is always less than or equal to h of x, you can see how g of x is essentially trapped in between f of x and g of x. So imagine if I take the limit of f of x as x approaches some value a, and I get L for that limit, and I take the limit of h of x as x approaches that same exact value a, and I also get L. If g is trapped in between, what do you think that limit has to be? That limit will also have to be L. So how we're going to write this out is if the limit of f of x as x approaches a is equivalent to the limit of h of x as x approaches a, and let's say that those both equal L, well, then the limit of g of x as x approaches a must also equal L. And that's assuming that g of x is trapped in between f of x and h of x. So what I've done below is I've made a diagram or a graph that shows this same exact concept. I have some green function and some blue function where each function is always, for example, within the negatives, my green function is always greater than or equal to my red function, and my blue function is always less than or equal to. Or when I'm in the positives, those flip-flop, so that red function is constantly trapped between the two. So if I looked at this as I approached from the left versus as I approached from the right, I still have that same function trapped between those two. So as I approach from the left and as I approach from the right, if they both go to that same finite value, then I know exactly what happens to that red function that's trapped in between. And this graph actually happens to depict example 1, which we're going to use the squeeze theorem to evaluate the limit of x times the cosine of x as x approaches 0. So we need to figure out how to trap x cosine of x between two separate functions. And I know for a fact that my cosine of x is always between two values. If you think about that unit circle, the cosine of x is always between -1 and 1. The cosine of x is never greater than 1 and never less than -1. So it's trapped between -1 and 1. Now let's say that I multiply this entire inequality by x. Well, then I'll have that -x is less than or equal to x cosine of x, which is less than or equal to x. So you can see how I didn't change the value because I multiplied x to everything. The same inequality still applies. Granted, if x was a negative number, obviously those inequalities would then switch, because when you multiply or divide by a negative, you switch the inequalities, but x cosine of x is still trapped in between regardless. So what I'm going to do is I'm going to find the limit of -x and the limit of x as x approaches 0, and if those equal the same, well then I know exactly what happens to that x cosine of x when I take the limit of that as x approaches that same value of 0. So I'm going to have the limit of -x as x approaches 0, and I know that that's equivalent to 0. Plug 0 right on into that linear function. Then I'm also going to have the limit of x as x approaches 0. Well, plugging that value of a right on into my linear function, I also get 0. So because each of those limits equals 0 and x cosine of x is trapped between those two functions, then I know the limit of x times cosine of x as x approaches 0 is also going to equal 0. And that is how the squeeze theorem works. You just have to show that those outer function limits are the same, then you know exactly what the limit of that function that's trapped between those two functions is equivalent to. And that's just a quick example of the squeeze theorem. So in this worksheet, we quickly went over limit laws and the squeeze theorem just to give you some more tools in your toolbox for when evaluating limits. And as promised in the previous video, in the next video that we're going to be doing, we're going to figure out how to solve for limits of rational functions where that denominator does not cancel out. So where we cannot cancel out that factor in the denominator that makes the function undefined. What do we do? How do we evaluate that limit? We'll find out in the next video. Continue on to that next example video, but until then, good luck with your online learning.